here for giving me opportunity to present our research work here. So this is the project actually where we start in a kind of heterojunction structure, and this project recently I have received from the early career ECRA core research grant. So I am Dr. Sobhyasachi Mukhopadhyay from SRM University AP, Andhra Pradesh in Vijayawada. So this is my brief outline of my talk, like why does organic inorganic heterostructure matters, electronic structure, band alignment and other things, carrier transport, optical properties of heterostructure, carrier transport properties, interface interaction, and then device level implication, and then conclusion. So when I start, basically I am organic electronics by passion. So when I start my lab here, and I was thinking, okay, what project I need to submit so that it will be some innovation or some novelty will be there. So I find out that now people are working on the organic inorganic heterostructure. So in this session, over the talks, I have heard many things where you have a Shivangi also work on, you have inorganic heterostructure, two-dimensional heterostructure. But what will happen if we mix organic and inorganic? Do we get any extra specific property on it, or it is going to help to us for make a device out of it? With this implication, actually, I wrote a project to NRF. At that time it was ACRB when I submitted the early career core research grant, but when I received the project it was under NRF. So I don't have like so much data like recently whatever people are presented in this session, but this project has been started in like a 1 year in my laboratory. So what we are planning to do actually here, we are bridging the world, the inorganic when it meets to the organic. So when we mix the organic, so inorganic we are thinking two-dimensional materials. So in that case what will happen, organics also it has to be have a same type of structure, otherwise there will be not match or lateral mismatch will not happen. So we took two materials, two-dimensional materials, which is the bismuth oxylenide, and then which is we know well known about the how to prepare it, and then from the organic side we have taken rubenin, because rubenin also very known actually is a two-dimensional small molecule, and we can make a crystal out of it. We can make a PVD, we can evaporate rubenin in an organic evaporator. So what we took bismuth selenide, because it's a two-dimensional layer semiconductor, it has a very good thermal and chemical stability, exponential charge carrier mobility, because there is already report where people use transistor out of it, and then it has a band gap optical absorption, people have developed photodetector with it, and excellent for carrier transport, photodetection and sensing. Lot of reports are there on this topic. And in other case, the other material which is organic one, rubenin, it also have some kind of planar structure, and then it has a high photoluminescence quantum yield. So tunable optoelectronic properties, and we can make it on the flexible substrates. It supports singlet fusion and other thing, and it's a pi conjugated organic molecule. So pi conjugation is always help for the optoelectronics properties. So now when we make the heterostructure, what we expect actually, so what we expect actually, so it has a enhanced charge separation and transport at the interface. Like if you make two-dimensional materials, one is organic and one is inorganic, you don't have the interface in that case, but when the interface is creating, it has to be have a more charge separation properties, like what we see in the bulk heterojunction organic solar cells, when you have a acceptor materials and donor materials, and the interface we have find a huge charge separation properties, and that's why we get a photocurrent in the organic solar cells. So that high bit excitation formation may create, but we don't actually experimentally it is possible to or, and then opportunities for the next generation application, and it has created a good platform to study the interfacial properties. So those are the properties we have mentioned. So recently there is a very lots of reports like with those kind of two-dimensional materials like electronic structure at the perovskite Rubinin interface, the effect of the surface termination. So they say that a lot of termination has been created in this case, and that's always create some kind of interfacial effect and interfacial property which is going to get a more photocurrent in your circuit. In the other report I have seen like photo-induced carrier dynamics, so which tell that they have a energy when they put a MOS and then pentacene type of, which is also two-dimensional organic electronics. So they have find out there is a lot of electron and hole separation when you shining the light in those materials. But it is to do those are the computational results, but is it experimentally has been possible? Yes, there is a group who has achieved that experimentally possible results. So what they have done on a two-dimensional materials, they have deposited rubinin. So first they created two-dimensional materials on the mica, and on the top of this molecule they took the substrates and then put it another PVD with the rubinin, which is called kind of organic thermal vapor deposition. So you evaporate organic materials and it finally goes and stick on the surface in presence of a airflow. So they have made a materials a detector like you have a gold electrode, and in between you have a heterojunction which is two-dimensional organic materials, and then inorganic materials is rubinin, and they have studied the optoelectronics properties at the wavelength is around the near IR, which we are important for the photo detector in our communication purpose. So they have reported also the dark and light current, we see order of 10 to the power 3 order of magnitude increment, and also with the shining of the laser light intensity, how the current has been changes, the DC current has been changes, and then the current magnitude, what is the responsivity of those detectors, and then what is the detectivity of those detectors. So detectivity, if you see, is order of 10 to the power 13 joules, and then responsivity also order of 10 to the power 3 order of magnitude. So it has a very low dark current and which can be used for the photo detector that at the IR scale. And if we make the devices out of those materials, maybe we can make a nice vision camera because it works in the IR region. So with this idea, we started with a motivation like we want to make a device out of it, like we want to make a indium tin oxide, then hole transporting materials, then the heterostructure, then electron transporting materials, and then the final top electrode. So the motivation is like we make these devices, but like which have a heterojunction interface designs, enable efficient charge transport, photo switchable, and the scalable next generation memory application. Along with the photon, we want to also use it for the memory application. I will come how we can going to use for the memory application, and then engineering low power, high performance, non-volatile memory application. So what is the hypothesis we are taking here? Hypothesis we are taking like it have an interfacial charge transfer, there will be dipole formation in the organic inorganic interfaces, and then electronic structure modulation at those interfaces, which will create the low resistance transport channels when we apply the voltage, and the vice versa will happen. And we can use as a low power memory devices application. So what is our device architecture? As I shown, our device architecture, we start with the ITO, then we have a ZNO, and then we have a rubinin organic semiconductor, or it can be vice versa also, and then two-dimensional semiconductor, molybdenum oxide, and then silver, because gold is very expensive right now, so we cannot go for the gold evaporation. So those are the work function and then Fermi level, and then what we expect, the electron injection from the ITO ZNO surfaces, and then the molybdenum oxide AU will have a high work function which will block those electrons to come on the surface. So in that case, what will happen, we have a charge localization at those interfaces which can be stored instead of applying bias. So this structure supports a non-volatile charge tap memory behavior where the charge will store in between the interfaces. So what is the alignment we have? We have a type 2 band alignment between the organic and inorganic materials, efficient charge tapping in the rubinin, because we already know that there is a lot of defects in the organic semiconductor, so it's going to trap the charges in that case. Strong interfacial coupling at those interfaces, low operating voltage, and suitable for maintaining high off-on ratio. So before we starting this project, actually when we have received the sanction order, we start, okay, before the starting can we do the computation study of these interfaces, so that when we have received the money, it will be going, or fund will receive, it will help us to understand what is the like what is the background has been hopping on at these interfaces. So even though as an experimentalist, I started learning like how the DFT works. Okay, so these are the DFT workflow we have utilized in the studies. So we use VAFs, which is accessible in our university, and energy coverage and other things. Some of the collaborators told me about how to do it, and then how to do the Billiard samples, and finally we find out the charge density work function and the dipole moment at the interfaces. So this is the summary what we have done actually. So first we developed the unit cell of the inorganic materials. So it's showing here actually. So we have like 4 barium, 2 cesium, and then oxygen, total 10 atoms we have taken in our calculations. And then for the rubenin cell, we started with the lower measurements, then we find out no, we are not getting the accurate band diagram. So we have to increase the number of molecules. We are working around like 280 atoms, but even it's only carbon and hydrogen, so it's not taking much computation power. So then we compare like what is the supercell, we are going to do it now. So for the supercell parameter, we find out it's coming around 3.98 angstrom for inorganic, and for organic we know rubenin is 2.26, so it will be little bit higher. So what we did actually, we have extend the rubenin over that. So we have extend the inorganic materials on the rubenin surfaces. And then B and C is almost matching, but we have to increase it 2 times, and here it 12 and then 14, so we don't pay much attention on it. So now after formation of this, when we are going to make a heterostructure, what is important? The lattice parameter we have to consider. So the lattice parameter match we have to find out. So along the x-axis we find out is around, when we make the sheet of the 2-dimensional or inorganic materials, we find out lattice parameter lattice mismatch is coming around 1.6%, and then along the c-axis is coming around 0.91%. So which will be reliable as per the publication we have seen in this topic. So then we have done the heterostructure, and this is that side view and this is the top view, and then finally we engage the cross-sectional view, and we find out when we optimize the structure, we find out the gap has been between around 2.64 angstrom, 3.24 angstrom. So then we calculate the binding energy of this heterostructure, and then we find out coming around minus 0.98. So this negative binding energy confirms that it's a spontaneous function, formation and structure is stable, and at the same time the interaction is governed by the van der Waals forces. So basically what we have developed a van der Waals heterostructure using a organic inorganic materials. So lattice mismatch summary is the lattice mismatch is less than 5%. There is a distance between the organic and inorganic, which at the stable condition, which is 3.24 angstrom. Binding energy negative is a stable function, and then these are the conclusion from our experiments. Then after this, we studied with the electronic structure calculations. So we studied first with the inorganic one, but we find out the energy level what we are calculating is 0.44, which is much smaller than the reported value, because we find out it's issue with the functional. So we started working with the DFT functional, and then finally we started with the PAB with the spin orbital coupling, and also we find out is coming around 0.3, but which is also not match with it. Then we go for the hybrid functional, and for the hybrid functional, when we calculated the density of states and the band function, we find out it's coming good, it's coming in around 0.81 instead of 1.5. So we optimize this structure. That is the best we can do now in this topic. And then after this, we go for the bulk measurements of the rubenin. We also find out the PDA, and then what is the band gap between it with the 2 different functional, and then finally we plot the dot. So after plotting this one, we studied the optimize the functional, and after optimizing functional, we studied the heterostructure. So this is the D, E and F is giving the heterostructure information. So D is the band structure, E is the total density of states, and then the partial density of state is shown here. So here we can see at the zero energy level there is a some kind of overlap of the partial energy of state. What is the cesium 4p, barium 4p, and also some of the oxygen has a partial energy level state at the zero energy level, which directly tells us there are some kind of electrons is moving from the interface in between the inorganic materials to the organic materials. So we try to study the charge transfer analysis, what is happening in here. So this is on the top is the electron charge density distribution layer for the different atoms we have find out, and we have plotted the cross sectional value of the charge density. What we have find out, along with the distance of the interface, there is a some kind of charge motion. And then we also calculated with the continuity of the charge, and we find out around 1.9 eV electron has been transferring from rubenin to the helium two-dimensional materials. We also find out the work function of the heterostructure. So for the bulk one, and then what happened in the heterostructure. So for the bulk, we find out for the two-dimensional organic one is inorganic one is 5.03, but when we go for the heterostructure, it is coming out 3.2. So which tells that there is some kind of interface and dipole is happening in between the heterostructure because of the charge motion, and which is lowering the lowering the work function, which will be very useful for developing the memory devices for this application. So then we try to find out like about the potential, what is happening at the interfaces. So what we find, so those are the bulk one for the inorganic one and for the rubenin one, and this is at the interface one. So the interface electrostatic potential distribution is shown actually in A and then B in the lower plot. So what shows that there is a voltage difference, is a spike like potential of a shift of 0.6 volt, indicating there is a built-in electric field or some kind of Schottky barrier is forming in this in these interfaces. And then this structure reveals the charge accumulation and the depletion across the interfaces, which confirming the dipole formation at the interfaces. So what is the summary we have received? Summary we have received the in case of summary, what we have find out, like there is a DFT observation, and then what is the relevance across the memory. So we have find out there is a binding energy changing, so which is going to help for the retention and the cyclic stability of those charges. Charge transfer is happening at the charge storage and the step assisted switching. There is a dipole formation, which is the internal field, and the directional transport is going to give us, which is essential for making a memory devices. And then work function shifting, which going to help us for the easier electron injection at these interfaces. And then there is a band gap, which we find out there is a small band gap, which we still don't understand yet, because it's kind of conducting nature, very low band gap. So what is the conductive channel is happening, and what is the physics behind it, we also still need to study. So then we study the optical property in the DFT measurements, following what we find out. First we calculated the dielectric function of those materials following those relations, and then we from the dielectric function, we calculated the energy loss function, absorption coefficient, reflectivity, exciton coefficient, and the reflective index of those materials at the interfaces. So here I summarize our optical property. So this is for the bulk one, this is for the also bulk for the rubenin one, and then this is for the heterostructure. So it's not exactly the straightforward addition, but what we find out at that interfaces, that we have seen some kind of extra absorption is coming up in the picture, which could be because of the rubenin structure. So following these calculations, actually now we have started doing the experimental measurements. So we are following the literature available protocol to develop the inorganic two-dimensional heterostructure. So we started with the precursor, and then finally during the hydrothermal process, we make those two-dimensional materials, and then finally we got a nano sheets of the two-dimensional materials. So we have done the XRD measurements. We have it's very matching with the pattern of what people have already reported for those measurements. And then we have done the XPS measurements till we are we have to do a lot of analysis on the study, so which is going to be happen. And then after this will be the future device fabrication. So for the device fabrication, the photolithography we are doing in the SENS IRC Bangalore, and then we are developing the organic inorganic evaporator in our devices through early career research grant, and with this we are going to make a device out of it. So how the device mechanism is going to work, or what is the physics behind it, actually what we understand. So when you make any memory devices, it has to be set, retention, and then the reset process. So when you have a set process, what we are going to do, actually we are applying a positive bias on the top electrode. And then what will happen, the electrons, when we apply positive bias on the top electrode, the electron will injected from here, and then due to the favorable band diagram at the interface, that those electrons are going to get trapped at the interface, mostly on the ruby side. So and then after this, what we are going to have, we are telling this is a kind of switching. So when the electron are going to stay on the ruby side, so basically it's going to create some kind of band, some kind of Schottky barrier, and the Schottky barrier is going to increase the resistance in those devices. So other direction will go, motion of electron is going to be stopped. So this we are going to retain when we are going to go for the lower voltage also, because it was trapped by at the interfaces. And then when we try to make it the erase process or the recess process, we have to apply reverse bias on the top electrode. So in that case, what will happen, the electron will repel again from the ITO, and then we are going to go for the higher resistance states. So this is the favorable band alignment, enable efficient charge transfer. The ruby here is going to act as the effective charge trapping layer, and then it going to have a very low operating voltage compared to the silicon, and then the switchable retention and the high off-on ratio that we are expecting on those devices. So currently the device fabrication under process. I thought, like, before I come, we are going to show some of the devices, but we tried of around 50 of devices, but we don't have luck actually on those matters. So maybe next time when we meet, I am going to show you the device characteristics and then memory application of it. Okay, so what are the key findings? So the key findings here we have from what we understood from our computation study, like we have a van der Waals heterostructure with this organic, inorganic, organic and inorganic materials. The charge transport induced dipole and the work function modulation at that interfaces, and the near metallic interfaces, which is still we need to understand the physics behind it, and at which is going to help us for the low voltage and the high retention of the RAM operation. And then we have synthesized with the nano sheets of these materials. So this work has been done with my PhD students who is with me. He is an international PhD student. He came from Ghana. He is working under this project, and I want to thank the organizer and also SRM University AP, and also like my funding agency ENRF for funding this project. Thank you for your kind attention.
Thank you. So let's have some questions.
Thank you, Professor.
Hello.
Some of the comment as well as some queries, because what I believe that in such attempt that you are trying to do DFT based on experiment is mostly it is better to experiment.
Yes,
I agree. That is one point. Secondly, look, I mean, having higher HEC calculation on bulk structure, there is no guarantee that you can do such calculation on a heterogeneous. It is absolutely absurd, because you cannot do it, because with 500 atom with spin orbit HEC on your model, you can never because that atom will completely destroy your initial control structure, what you have seen, is complete hybridization in the interface to the under all geometry that we have created. And that part is extremely challenging to understand, extremely, in a particular case. And overall, finally, what I believe that, yes, silicon is a old technology, but possibly much, much cheaper than I produce such kind of heavy metal waste. So why not? I mean, we should try the fundamental silicon with the Ruben. If we really find out some problem, operating condition, what is what you mentioned, possibly it's better than to think some higher order,
Higher
like
order.
kind of elements like this amount or all these things. So this is just
Sure,
to
thank you.
that it would be interesting for your design. So overall, but it's a good attempt. It's a novel interest. Thank you.
Nice talk. One question about blueprint. Itself is a switching material in
Hmm.
most of the boards in the past. So with the interface between the VI2 to AC and blueprint, what is the difference? I mean, how you expect the retention and
No, actually, yeah. So when people have developed that field effect transistor with the rubenin for the switching purpose, they have to use a single crystal rubenin. So here we are going to use some layer of the rubenin. So that is the difference actually.
but there are also reports where you have this vapor deposition of blueprint
Mm-hmm.
and then it shows
Yes, there is a report, but the thickness of the films actually are different compared to what we are planning for it actually.
in your case on zinc oxide, the VI2 to AC is spin casted and how do you transfer the material?
Yeah, so what we have planned actually, we are going to spin coast actually. Spin coast on the rubenin will be vapor deposited. Yes, thermally deposited.
Thank you very much.
Thanks for the talk. Thanks for the talk. I have an experimental question.
Mm-hmm.
So, some of these organic molecules, when you try to deposit on 2D materials, they don't spin coat very well. They
No.
get attached to like defect sites or.
Organic molecules, that rubenin, we have to do that thermal evaporation actually. We cannot do the spin coating.
Okay.
Only like semiconducting polymers that you can spin coat, but organic molecules you cannot do the spin coating.
So when you try to thermally evaporate these molecules, are there studies on how well they adhere to the TMDs? Or
Yeah, there are studies, but thing is that when again you are doing the measurements, actually you have to do lot of FTIR measurements to find out it's actually there or not. So now we are in a process to finding out like what are the thickness and how much layer has been deposited. So we have made a PLD with the argon gas actually, but now we are optimizing the flow of argon gas. What is the control rate of temperature? So that needs lot of optimization. And what happened following the reported value, actually you cannot exactly use it because it depends upon it varies from different lab to labs. So that is the main issue, and that needs lot of optimization. That creates lot of kills lot of time actually. Maybe he knows actually, Ashish knows like how much time is required.
one last question? If not, then let's thank
Thank
the
you.
speaker again. So let's thank also all the speakers for this session for being on time.